Just getting ready here. We're just giving the late guys a second to get in. Okay. So the idea here today is to look at two-dimensional collisions and problems that happen. And then we want to look at our lab setup. Okay, so here's what's going to happen. So what's going to happen today is I'll go through the last type of problem that we're going to look at with momentum, and that's two-dimensional ones. Then I'll kind of talk about the lab a little bit, what you need and stuff. Tomorrow I have a practice sheet with momentum and impulse on it. You're going to work on that. While you're working on that tomorrow, I'm going to set up the exploding cart lab and demonstrate it while you're working on practice problems so that you can see what I'm talking about. And I'm going to do a couple of them here in Vanguard to show you what it looks like, okay, on camera, so that everybody will have an idea what I'm talking about. And then on Monday, when we get back and everybody's seen me do one example and stuff like that, what you need to do, okay? And then we're gonna do some exploding carts. Now, if you don't have any exploding carts in the school, that's okay. I'll do a few examples on that practice day on Friday. And I can post up the results, what they look like, and then you can analyze those if you don't have an opportunity to explode your own set of carts. But here in Vanguard, we'll do one per person, and it's fairly easy to do. Okay, so that's the long-term plan of the class in the next 3 or so days. So today that means we're going to look at the two-dimensional momentum problem. Now we can only look at, we only look at one particular type, and that's right-angle collisions. Okay, so that's right-angle collisions and how they translate into two-dimensional momentum problems. So that's what we're going to start with today. Okay, so let's just start up with a two-dimensional problem and work it through step by step. Okay, so let's say that this is going to be a right angle 2D momentum example. Okay, how we work and analyze it. So let's say we've got a car with a mass of, let's say, 1,050 kilograms, traveling at, let's say, we'll go 3 significant figures, we'll say 85.2 kilometers per hour to the east. Okay. And it collides with we'll call it a truck so that we have a different thing, with a mass of, let's say, 1,540 kilograms, traveling at, let's say, 71.5 kilometers per hour. And we'll say south. Okay, so there's our setup. Okay, after the collision, we'll put, so that's the before part. After the collision, the wreck sticks together, we'll say. Okay. Find the velocity of the wreckage. Okay, so this is basically going to be a vector momentum problem combined together kind of idea. So the first thing we're going to do is we're going to set up what's happening in a diagram so we can view it. Okay, momentum will be conserved if we don't lose. Now, in a actual collision, you'll lose some energy with compression areas and things like that. So this isn't 100% realistic, but it's close enough. It'll give us the velocity right after the collision, but not, as it slows down and things like that. But it'll give us the immediate velocity right after they collide, because there wouldn't be as much compression and things like that. Okay, so the first thing we're going to do is draw it out. So I'm going to use my arrows here. We've got in our x direction, we've got our car going to the east, and here we'll say we have our truck coming from traveling to the south. Okay, now they're going to collide together and go some direction like this, depending on the momentums. We don't know exactly where it's pointing, but somewhere in there. Okay, so we know that we've got our car, pardon me. We've got our mass of our car and our velocity of our car. So that would be, this is our x direction. Okay, so we can kind of figure that out by multiplying 1150 and 85.2. Kilometers, per hour. Okay, so that gives us our momentum before. Okay, we can do a similar thing with the truck as well. We've got our y direction. Okay. Well, if we're looking at our y direction, we're going to combine the mass of the truck and the velocity of the truck to get our momentum. So that's 1540 times our velocity of 71.5. Now that's going south. So we can, if we want to keep track of directions and stuff, we know it's going downwards, negative direction, but we can do that when we combine them. So this is our initial momentums. So we've got an initial momentum in the x and initial momentum in the y. Okay, so let's combine them with our calculator and calculate them out. So let's take the 1150 times 85.2. Okay, that's 97,980. Okay, and that's kilometers per hour. Okay, and then that's 1540 times 71.5. That's 1. And we've got this is our y. Okay, this is kind of going down, and this one's kind of going to the right. So after the collision, the wreck is going to have the same y and x momentum, but its mass is going to be combined into one vector. So we're going to combine the two vectors to make a resultant vector to get our total momentum. So our total momentum is going to be combined. So if we're going to get our total momentum, we have to do vector addition. Okay, we could do sine and cosine law if it's not right angles, but generally speaking, I stick to right angles so that we have our right angle idea. So if we draw it out to get our total momentum, let me just do an arrow that's not dotted. So let's say that one and this one. This one's a little bit bigger. So there's our momentum. This one here is 97,980. And this one is 110,110. Okay, so then we can get our total momentum before. Okay, so we just go this one squared plus that one squared. It's a right triangle. This will be our R. Okay, take your calculator out. Square 110, 110 plus 97, 980 squared. Okay, you get a huge number. Okay, somehow I multiplied mine. Let me do that again. 110, 110 squared plus 97, 980 squared, okay, equals, and then square root it. So I get my total momentum when I square root that 147,392 to the nearest whole number. And that's kilometers per hour. Okay, so that, now we're only going to be ending up rounding it off to 3 significant figures, but we'll keep those numbers for now. Okay, so that's our initial momentum. Okay, but we do need, in terms of the size, but we need to find a direction. So that we can say that our momentum is that, so much to the east, so much to the south. We need a direction so that we know which way that this line is actually pointing. So to find a direction, we're just going to do tan. Yep.
On your second diagram, though, 110,100 is just the second last digit to 0 instead of a 1.
Oh, it's supposed to be 1110. Oh, dang it. One 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 zero. Oh, there goes my last sticker. I got one left.
Please get started.
I have to get a new one.
Thank you.
There you go. Okay, yeah, it should have been there that way. I did it right over here though, so that's okay. Okay, so now we're going to do tan inverse, and we'll get this angle up here. Okay, so we're going to go opposite over adjacent. So 110, 110, opposite over adjacent. Okay, and that's going to equal our theta. Okay, so I take my calculator out, and I do that. Okay, so inverse tan, make sure it's in degrees, shift tan. Okay, bracket. 110 divided by 97,980. Close my bracket. I have 48.3 or 48 degrees. So that tells us what would our initial momentum be for each of those when we combine the X direction car and the Y direction truck. So my total momentum is 147,392 kilometers per hour, going east 48 degrees to the south. Okay, now that we have the initial momentum, the final momentum is going to be the same. So since momentum is conserved, we know our final momentum is the same value. So that's the secondary part of this. So since momentum is conserved, after the collision, we have the same momentum. Okay, or momentum value. So we can use this number, and then we can calculate its velocity because we know that the wreck is stuck together. Okay? The wreck is stuck together, so we can combine the mass. So we know that this is our momentum, so the final momentum is going to equal the mass of the wreck times the velocity of the wreck. Okay, and there's only one object because it sticks together. I mean, if there was two objects, we'd have to break it apart and do another vector analysis, but that involves a lot of complexity. So we usually don't go that complex in grade 12. You may, when you get into further studies, if you do further studies in physics. Okay, so this is going to be our 14,392. Our mass is going to be the combination of our car plus our truck, which was, what was it, 1540. And then we're having our velocity. Okay, and reminding ourselves that this is east 48 degrees south. So that this direction and this direction will be the same. Okay, take our calculator out. We're going to add these two numbers together and divide it out here. So 1150 plus 1540, that's 2690. Okay, and then obviously what will be left will be kilometers per hour with the proper direction. And we're going to round it off to three significant figures now for our final answer of the velocity of the wreck. Okay, what would it look like? Okay, we take 147,392 and we divide out with our calculator 2690. Okay, I get 57.79. So that's going to be 54.79. So to three significant figures, 54.8 kilometers an hour. And of course, we have the same direction as our momentum. East 48 degrees south. Okay, so that is an example of two dimensions. So this is a specific two-dimensional example. It only works when we're doing right angles because we're using right angle technique. So what are our basic steps here involved if we look back at the beginning? Okay, firstly we get the x direction and the y direction momentum by multiplying the mass with its velocity. Once we have the x and y direction, we combine them using right angles to get the magnitude of the vector that they add together, or as we used to call it, vectors, the resultant. Okay, then we find the angle that it's traveling at by using tangent. Once we have the resultant vector with its angle, we can then assume that the final momentum is going to be equal to the initial momentum because it's conserved. in the system. If we assume that and we know that the mass is combined, we then just equal that initial momentum to the final momentum and put in the given masses to find our missing velocity. And that's the basic ideas of a right angle collision problem. Now, you can also have an explode problem as well, where something will explode apart, and we'll look at one of those as well. Any questions on that one? Okay, very similar to our vector one. In terms of exams here, I imagine that I'll be able to get them back to you fairly soon. I looked at them, they look fairly good, so I'll go through them and get them back to everybody. I think I have maybe 1 or 2 people left to finish here, and then we're good that weren't here yesterday. So that'll be happening hopefully this week. All right, so that's the first idea. Okay, secondly, this is probably where I'll stick. So secondly, what I'm going to do then is I'm going to set up our lab that we're going to do. Okay, so tomorrow I'm going to demonstrate this while you're practicing. So basically, here's the diagram for your lab setup. Okay, and I kind of set it up. I'll probably set it up here in Vanguard on the front counter there for us to use it, and then it'll be set up for everybody to use. And then I can turn my camera around and show everybody what it looks like while everybody's working tomorrow. So okay, so the first thing is you need 2 carts, some masses, and 2 ticker timers. So what you usually do is you set up your carts back to back. Now you have to know the masses of the carts. So this one here is like, let's say it's 2,040 grams. And let's say that this one here is only 1,600. Okay. And then what you do is, when my carts have little edges on them like this. Okay, so you need a ticker timer here. So if this is your tabletop, okay, over here you'll have your ticker timer, and you'll tape a tape to there. So that'll be sitting on the table beside your cart. Now, sometimes what I do is I take a book and I put it on a book so it's a little bit higher. Okay, and then sometimes it'll rip if there's too much of an angle when it explodes. Now this one, oops, sorry. Because this is going to be, this one goes to the far one. It's taped to this one. So this one's, if this is A, this is A. Because it's going to go this way. So you want the ticker tape to be pulled that way. Okay, then you're going to have your other ticker tape will be over here. And you're going to, if this one's B, you're going to have your ticker tape so when they explode, this ticker tape is moving to the right, and the red ticker tape is moving to the left. Okay. And how do you explode them? There's usually a button to push. Don't use your finger. Push button, because what you do is you take a meter stick and you crack it. I'll show you that tomorrow. When I'm going to do a demonstration on camera tomorrow when you're working on what it looks like, so you'll see it. Now, depending on your cart, usually you just tap the button with a meter stick so that you're not touching the button too long and slowing it down. Okay, once you've done that, you'll get ticker tape B. You'll look for 6 dots at the very beginning. And you'll measure 6 dots. Okay, so you're going to measure the first 6 dots. Now, if there's a bunch that are all kind of stuck together, just start on the first clear one. Okay? Measure the first 6 dots. Okay? Ticker tape A. Same thing. Okay, so let's say that this one was 3.2 centimeters. And let's say that this one was, let me just check that. Okay, no worries. Okay, and let's say that this one was, I don't know, let's say it was 2.1 centimeters. Okay, so that's what you do. You're just going to look at the very beginning of the tape. There'll be a whole bunch of tape there. You don't use a lot of tape. You just need a little section of whatever it's going to be because you want the speed at that first tenth of a second. Okay, so 6 dots will be a tenth of a second if you have a 60 hertz timer, which most timers are 60 hertz or 50. If you have a 50 hertz one, that's okay. It'll still be close enough. You'll get the same error on both ends, so it won't matter. As long as you have similar ticker timers and not completely different ones. Okay, so what you do then is after you get these pieces, you would put the mass on the back so you don't forget. So the blue one would be 1,600 grams. And the red one would be 40 grams. Okay, so now you've got the mass of the cart. Now, how do you measure the mass of the cart? You use scales. Now, here in Vanguard, some of the scales aren't big enough because they weigh quite heavy. So we have to use a fishing scale to do it that way. But what I ended up doing is I did that years ago. I've been here for 28 years in Vanguard. I did that years ago, and I put the mass of every cart on. I put the mass of every cart and tape on it, so we don't have to do it here. But if you're not from Vanguard, you have to get the mass somehow. To the nearest 10 grams is good. Doesn't have to be right on. All right. So, having said that, now that you've got these two things, you then calculate them. Now, according to theory, the momentum of B and the momentum of A should be equal to each other in opposite directions because they were starting from rest and had 0 momentum to start. So then the first thing you would do is get the speed of your tape. So you get the speed of each tape. So 6 dots equals 1/10 of a second. Okay? If you did 3 dots even, it might be okay, depending on how clear they are. Okay? I usually go 3 or 6 dots, but we'll try 6 dots to start. Tomorrow when I'm doing demos, I'll take a look at it and see if 3 is a better idea or not. But it doesn't matter. We'll say 6 dots. So then you would find the speed. So if I'm doing the velocity of cart, the blue one I called cart B, okay, that would be the distance divided by the distance of B divided by the time. So it'd be 3.2 centimeters divided by 0.1 seconds equals 32 centimeters a second. Okay? And the velocity of A, that's going to be 22.1 centimeters divided by 0.1, 21 centimeters a second. Okay, so that's how you get the initial velocities in your trial. Now you'll be able to compare against each other. Like in Vanguard here, we got like 13 or 14 people. So we'll have 13 or 14 trials. In the other schools, you might have 5 or 6, however many there are. Okay, and then you just do the momentum. So then the momentum. So then you just take the mass, this is B, so you need the mass of B, which would be 1,600. And 32 centimeters a second. Okay, take your calculator out. And I get 51,200. Okay, so that's the momentum of cart B. Okay, we do cart A over here. Okay, we're going to use this speed and the heavier mass. Okay. Now, when you're doing this with your class, don't have everybody explode empty carts, because then everybody's going to have the exact same thing. That's not good science. Good science is to put a weight on one of them, make it a little heavier. Put a 100-gram weight on one to make it a little bit heavier. Put a 200-gram weight on one. Okay? Mix up the masses a little bit. Okay? 20, 40, and I'll show you tomorrow when I'm doing some demonstrations. So 20, 40 times 2,100. Okay, so I've got 48 or 42,840. Okay, significant figure wise, probably should only be doing 2 figures just because of accuracy of things. So if we go 2 figures, let's say that this is 51. And this one's going to be 43. Okay, and then you can see you can do a percent difference here. So how far were you from them being equal? Okay, percent difference is the large one minus the small one over the average. Times 100. Okay, so the average of these two. Now, if you don't want to do significant figures and you just want to do the raw data and then round off at the end, that's okay too. But I'm thinking because of how we measure with and how accurate we're going to be, 2 significant figures is probably good enough for our lab. So if we do our calculation here, 51,000 plus 43,000 divided by 2. Okay, that gives us an average of 47,000. So we got 8,000 over 47,000 times 100. Okay, so 8,000 or 8 divided by 47. We got about a 17% error. I think you guys will get a little closer than that. I just made that one up without any raw data. Okay, so getting the raw data will be Monday. Tomorrow we'll do some practice stuff, working on practice problems. I'll be online with you with the camera turned around on my table. I'll just set it up where we can see it, and I will do a couple of trials to show you how it's done. And then I will do a few more trials in case there's a school that doesn't have the appropriate stuff that they need, so that I can post it up online and they can analyze that. So that's the general idea of what we're going to do here. Okay. Okay, so let's go back to the beginning, see where we were. Okay, we got that one, we got that one. Okay, so let's finish off today with, see if you can do a two-dimensional one. And that's where we'll start tomorrow. So in the last 10 minutes or 15 minutes, whatever we got, try this two-dimensional problem. And that's where I'll leave you for today. And then I'll post the solution at the beginning of tomorrow online with you, set up the lab. The practice stuff will be on will be printed out for you, or it'll be posted to the Google Classroom. And I'll have the lab stuff set up, and we'll be able to show what we're going to do on Monday. So that's the general idea. So try this one here. Let's say that we have, calculate the final velocity of the wreck when two cars collide at right angles. Okay. Okay. Okay, we'll just call them car A and car B. Okay, car A is 54 kilometers an hour west with a mass of 995 kilograms. So three significant figures. Let's make this 54.0 so that we have three significant figures. Okay? And car B, sorry. Okay? And it's going 88.0 kilometers an hour. North. Okay, and it has a mass 1,080, so three significant figures, kilograms. Okay, and they stick together. All right, there you go. So that's the last thing we're going to do today. You can work that through. And next day we'll get into that. There'll be some practice stuff. And also I'll be doing some demo of the lab, and you'll see how it looks. And then Monday we'll get, you can, if you have to find something, you can maybe run around on Friday and look for something as well while we're working on practice type stuff. Okay. All right. So you can work on that. I'm going to post this up. So I'm going to stop the video at this point.